Welcome to the Power Electronics class. Myself B. Veeranarayana, Senior Assistant Professor, Department of Electrical and Electronics Engineering. We are in third unit, AC to AC regulators and cycloconverters. We already completed the AC to AC regulators. Now we will go through the cycloconverters. Here the unit outcome, at this end of this lecture, you are going to analyze the operation of cycloconverters. And the contents of the cycloconverter, here you have step-up cycloconverter with R load and step-down cycloconverter with R and RL load. Under step-down with RL load, we are discussing both continuous conduction mode and discontinuous conduction mode. Later we concentrate on 3-phase to single phase and 3-phase to 3-phase cycloconverters. At this end of this class, the learning outcome, you are going to explain the operation of or explain the principle of step-up cycloconverter, and learning outcome 2, explain the operation of single phase step down cycloconverter. So first we go through the cycloconverters. Here the cycloconverters are simply called the frequency changers. These cycloconverters are the thyristor based converters which are used to convert power at one frequency to power at variable frequency with constant magnitude. If you go through the AC voltage controllers, those are used to convert fixed AC voltage to variable AC voltage without change in the frequency. But if you go through the cycloconverters, these are simply called the frequency changers. Here we keep power at one frequency to power at variable frequency. That means magnitude level should be constant. Whatever the input voltage you provide to the cycloconverter, the same output voltage should be collected, but the frequency level should be changed. Before inventing the power semiconductor devices, if you want to collect the variable frequency to control the speed of the AC motors, simply we depends on alternators. By changing the speed of the alternator, we are able to change the frequency. But if you go through this, after inventing the power semiconductor devices, the variable frequency should be collected by using these cycloconverters. Depends on the output voltage. The cycloconverters are mainly classified into two types. Depends on the frequency level, these cycloconverters are classified into two types. Those are, first one, step-up cycloconverter, and second one, step-down cycloconverter. If we go through the step-up cycloconverter, here the output frequency is greater than the source frequency. And if we go through the step-down cycloconverter, the output frequency is less than the source frequency. Depends upon the frequency level, we will classify as either step-up cycloconverter or step-down cycloconverter. And depends on the circuit configuration, these cycloconverters, both step-up cycloconverter and step-down cycloconverter, together classified into two types, depends on the circuit configuration. Those are midpoint type step-up cycloconverter or midpoint type step-down cycloconverter. And second one, bridge type, either step-up cycloconverter or bridge type step-down cycloconverter. And from the construction point of view, there is no difference between step-up cycloconverter and step-down cycloconverter. The same midpoint type converter can be used either step-up cycloconverter or step-down cycloconverter. Depends upon the changing of sequence of triggering of the SCRs. The same midpoint type converter can be able to operate either step-up cycloconverter or step-down cycloconverter. That means from the construction point of view, there is no difference between step-up cycloconverter and the step-down cycloconverter. And similarly, if you go through the bridge type cycloconverter, the same configuration can be used either step-up cycloconverter or step-down cycloconverter. We will discuss what is the midpoint type cycloconverter and what is the bridge type cycloconverter, circuit configuration and operation, how you are able to collect the step-up frequency and step-down frequency will be discussed. So first we go through the midpoint type step-up cycloconverter with R load. Yeah, here coming to the circuit diagram, yeah, this is the circuit representation of midpoint type step-up cycloconverter, and the circuit consisting one isolation transformer whose secondary winding is provided with the center tapping, and 4 ideal SCRs which are numbered as P1, N1, P2, N2. Out of these 4, P1, P2 are the positive group SCRs, N1 and N2 are the negative group SCRs. P1 and P2 are the positive group SCRs, N1 and N2 are the negative group SCRs. Right. Next, here I just want to collect F0 is equals to 2Fs. And here we have the source voltage like this. Here it is VA0 and here it is VB0. Here I just want to collect the output frequency F0 is equals to 2Fs. So here, for example, the source frequency is considered as Fs is equals to 50 Hz. If you choose the source frequency is 50 Hz, then what is the time period? 1 by F, which is 20 milliseconds. Out of this 20 milliseconds, 10 milliseconds is the positive half cycle and 10 milliseconds is the negative half cycle. Now I just want to collect the output frequency like 100 Hz, which is 2 Fs. Then what is the time period here? T is equals to 1 by F now. Then 10 milliseconds. So what is that meaning of 10 milliseconds here? 5 milliseconds is the on time or positive half cycle, and one more 5 milliseconds is the negative half cycle. So if you maintain in the output voltage waveform, for 5 milliseconds is the one positive cycle and 5 milliseconds is the one negative half cycle, then within 10 milliseconds we are going to complete one full cycle. How many cycles are there in source? For Fs is equal to 50 Hz, to complete the one time period, one complete cycle, 20 milliseconds. That means here this one is the 10 milliseconds and this one is the 10 milliseconds. Now between this 0 to 5 you complete one positive cycle, and next 5 to 10 one negative cycle, and 10 to 15 positive cycle, 15 to 20 negative cycle. Here if you want to collect F0 is equal to 2Fs means for completion of one full cycle in the source voltage, we are able to collect the two complete cycles in the output voltage waveform. Corresponding that you need to provide the gate pulses to the thyristors. So here during the positive half cycle of the supply, what happens here? This one is taken as A, and this is B, and this is C, and it is D, it is E, and here O. So tell me, during the positive half cycle what happens here? During the positive half cycle of the supply, terminal A is positive and B is negative. Corresponding that P1, N2 are in forward bias. Why? Because see here, P1 anode connected to the positive terminal, forward bias. N1 cathode connects to the positive terminal, reverse bias. P2 anode connects to the negative terminal, reverse bias. N2 cathode is connected to the negative terminal, forward bias. So during this positive half cycle, P1, N2 are in forward bias. At omega t is equal to 0, we provide the gate pulse to the P1. Then from 0 to pi, T1 will be in the on state. If P1 will be in the on state, the source VA0 is transmitted to the load, and current flow through the circuit is given by, see here, A plus T1 C E R O minus and A. In this manner, the current will be flow through the circuit, and the output voltage simply follows the VA0. What is the VA0 here? This one, and observe here, this is considered as the omega T1. At omega T1, by using some external commutation circuit, we forcibly reduce the current flow through the P1 is 0. Why I call forced commutation means actually the AC voltage, the cycloconverters are energized by the AC source. Even though the cycloconverters is energized by the AC source, especially in step-up cycloconverter, we need to use the forced commutation. Actually, where we prefer the forced commutation? Whenever the circuits are energized by the DC source, then we prefer the forced commutation. We will forcibly reduce the current flow through the SCRs below the holding current. If the circuits are energized by the AC source, then line commutation or natural commutation is sufficient to turn off the thyristor. But especially if you go through this step-up cycloconverter, even though the circuit is energized by the AC source, you need to use the forced commutation to turn off the thyristor. So at omega T1, by using some external forced commutation circuit, we will turn off the P1. After omega T1, what is your requirement? Negative output voltage. What is the negative group S here? During the positive group, positive source voltage, which is the negative group S here, comes to the forward biasing mode, N2. So, we provide the gate pulse to the N2. So, N2 comes to the on state. If N2 is in the on state, then what is the current flow through the circuit? From this O plus, R, E, D, N2, B minus, and like this. Observe, if P1 is in the on state, the current flow through the circuit from E to O, which is positive. If N2 is coming to the picture, then what is the current flow through the circuit? O to E, which is in opposite direction to the previous one. So, in this manner, the current will be flow through the circuit. Then, output voltage simply equals to the VB naught. What is the VB naught here? So, you follows this one. So, this is omega T1. This is omega T1. Here, this is the output voltage, like this. And here, this one. This one. Here, this is due to the conduction of P1 and it is due to the conduction of N2. Next, from pi to 2 pi, we have the negative voltage. We have the negative voltage across the thyristors. So, what happens? During the negative half cycle of the supply, here terminal A is negative and terminal A is negative and B is positive. If terminal A is negative and B is positive, corresponding that P1 is in reverse bias, N1 is in forward bias, P2 forward bias, N2 reverse bias. So, here during this negative half cycle, N1, P2 are in forward bias. So, if you want to collect the positive output voltage, then you need to provide the gate pulse to the positive group S here. If you want to collect the negative output voltage, then you provide the gate pulse to the negative group S here. See here, after pi, what is your required voltage? This one. Here like this. So, at omega t is equal to pi, you need to provide the gate pulse to the positive group S here. So, during the negative half cycle, N1, P2 are in forward bias na. So, you need to provide the gate pulse to the P2. If P2 comes to the on state, the lower half VB naught is transmitted to the load and current flow through the circuit is B plus P2 D E R O minus. Again the current will be flows from E to O na. So due to the conduction of P2, then we follows the VB naught. So this portion is available across the load. Then what is the output voltage here? Simply this one. Here this is due to the conduction of P2. Due to the conduction of P2. Next, at omega T2, by using some external force commutation circuit, we turn off the P2 and we provide the gate pulse to the negative group S here. What is the negative group S here? Here N1. So at omega T2, by using external force commutation circuit, you turn off the P2 and you provide the gate pulse to the N1. Then if N1 comes to the on state, the upper half of the source voltage is transmitted to the load and the current direction is given by here O plus R C N1 A minus and like this. See here, if N1 comes to the on state, then what is the current flow through the load? From O to E, which is in negative current, and output voltage simply follows VA naught na. So VA naught is this one. So this is the output voltage here due to the conduction of N1. So it is P1, N2, P2, N1. And again we have the positive cycle. Again you conduct P1, N2, P2, N1. In this manner, if you provide the gate pulses and you turn off the thyristors, we are able to collect the output frequency, which is the 2 times to the source frequency. If you take F0 is equal to 2Fs, then this is the output voltage representation. Very simple. If you go F0 is equal to 2Fs means for completion of one full cycle of the source voltage, in the load you have 2 cycles. See, this one is the one cycle and this one is the second cycle. That is the output voltage representation. And this notation is very important. 0 to omega T1. P1 is in the on state. Omega T1 to pi. N2 is in the on state. Pi to omega T2. P2 is in the on state. Omega T2 to 2 pi. N1 is in the on state. That is the output voltage representation. Right. Now, I just want to draw the output voltage waveform for F0 is equals to 4Fs. F0 is equal to 4Fs. Then, just we try to draw this output voltage. First we take the source voltage. This is pi, 2 pi, here Vm, and it is Va naught, it is Vp naught. So what I said here, during the positive half cycle of the supply, P1, N2 are in forward bias. During the negative half cycle of the supply, P2, N1 are in forward bias. Right. Now, I want to collect F0 is equal to 4Fs. What is that meaning? For completion of one full cycle of the source voltage, you are able to collect the 4 complete cycles of the output voltage. 4 complete cycles means in positive half cycle 2 complete cycles and a negative half cycle 2 complete cycles. So, this one is the one half cycle and this one is the another half. In this half, you are able to complete positive cycle, negative cycle, and you divide this negative half cycle of the source voltage into 2 halves. In this, you need to collect the positive portion and the negative portion. See, at omega t is equal to 0 during the positive half cycle of the supply, P1, N2 are in forward bias, N1, P2 are in reverse bias. At omega t is equal to 0, I just want to collect positive output voltage. So, you need to provide the gate pulse to the P1. Then, up to this is taken as omega T1. Up to omega T1, we need to maintain the on state of the P1. Right. At omega T1, by using forced commutation circuit, we turn off the P1 and we provide the gate pulse to N2. We provide the gate pulse to N2. Then what you are getting here? N2 means we follow the VB0 up to this one, up to omega T2. Up to omega T2, we maintain this N2 is in the on state. And at omega T2, by using forced commutation circuit, we turn off the N2 and we provide the gate pulse to the P1. Then again you follow the Va0 like this up to omega T3. And at omega T3, by using forced commutation circuit, we turn off the P1 and we provide the gate pulse to N2. Then like this, N2. So, for completion of one positive half cycle of the source voltage, we are able to collect the 2 complete cycles. This one is 1 and this one is 2. In this manner, you need to design the firing circuit and forced commutation circuit. That is the big task. And see here, during the negative half cycle of the source, P2, N1 are in forward bias. Then you need to control P2, N1 switches. What is the requirement here? Positive source voltage. What about the source? Negative. Then you need to trigger the P2. So at omega t is equal to pi, we provide the gate pulse to the P2. Then we follows the, here what is the required voltage? Positive voltage. During the negative half cycle, P2, N1 are in forward bias. So if you want to collect this positive voltage, then you need to provide the gate pulse to which one? Yes, P2. Then like this, omega T4. Here P2 will be in the on state. And here we just need to collect the negative output voltage. Negative output voltage. Then you need to provide the gate pulse to the N1. Then this one at omega T5. And similarly this one and this one. Clear? So this is the simple representation of output voltage waveform for F0 is equals to 4Fs. So output voltage, just you need to redraw like the output voltage here, this one, like this. Here this is due to the conduction of P1, N2, P1, N2, and again here P2, N1, P2, N1. That is the simple representation of output voltage. If P2 is in the on state, simply we follow the VB0. If N1 is in the on state, we follow the VA0. Why? Because P1, N1 are related to the VA0, P2, N2 are related to the VB0. Yes, this is a simple representation of F0 is equal to 4Fs, and these are the output voltage waveforms for midpoint type step-up cycloconverter. And if you go through the bridge type cycloconverter, single phase bridge type step-up cycloconverter with R load, then the circuit diagram becomes this is P1, P2, P3, P4. This one is N1, N2, N3, N4. Here you have Vs is equals to Vm sin omega t, and here we have the R load, and here you have the output voltage. So this is simply considered as P converter, and this is simply considered as N converter. And if you go through this single phase bridge type step-up cycloconverter, I just want to collect F0 is equal to 2Fs, first case. I just want to collect this output voltage waveform. F0 is equals to 2Fs. Then what happens here? During the positive half cycle of the supply, this is taken as A, B, and this is considered as A dash, B dash. During the positive half cycle of the supply, what happens? Terminal A is positive and B is negative. Terminal A is positive and B is negative. Corresponding that P1, P2 are in forward bias, P3, P4 are in reverse bias. So during this positive half cycle, P1, P2 and out of this N converter during the positive half cycle, this is positive and this is negative. Which are in forward bias here? N1, N2. N1, N2. So during the positive half cycle of the supply, P1, P2 and N1, N2 are in forward bias. Similarly, during the negative half cycle of the supply, P3, P4 and N3, N4 are in forward bias. So during the positive half cycle, if you want to collect the positive output voltage, you need to provide the gate pulse to P1, P2. And if you want to collect the negative output voltage, you need to provide the gate pulse to N1, N2. Similarly, during the negative half cycle, if you want to collect the positive output voltage, you need to provide the gate pulse to P3, P4. And you need to provide the gate pulse to N3, N4 if you want to collect the negative output voltage. Then what happens here? If you go through this bridge type cycloconverter, the output voltage should be same. But instead of single SCR, in bridge type, we have the two SCRs will be comes to the on state. Those are, instead of P1, here you have P1, P2. Or we will redraw these waveforms. Don't confuse. Just stay here. I just want to collect the output frequency 2 times to the source frequency. So here I am taking the source voltage like this, and this one is VAB, and this one is VBE. Then what is the output voltage here? From 0 to pi during the positive half cycle of the supply, P1, P2 are in forward bias, N1, N2 are in forward bias, P3, P4 and N3, N4 are in reverse bias. I just want to collect the positive output voltage, this one, up to omega T1. You need to maintain the on state of P1, P2. At omega T1, we commutate this P1, P2 and we provide the gate pulse to N1, N2. If N1, N2 are in the on state, what happens? This is the current flow through the circuit. N1, see, load, N2, like this, source, and this one, in this manner. So, during the positive half cycle of the supply, if you want to collect the negative output voltage, you need to provide the gate pulse to N1, N2. And during the negative half cycle of the source voltage, what are the forward bias SCRs? P3, P4 and N3, N4. If you want to collect the positive output voltage, you need to provide the gate pulse to P3, P4. And if you want to collect the negative output voltage, you need to provide the gate pulse to N3, N4. So what happens here? I just want to collect the positive output voltage up to omega T2. Then you need to maintain T3, P4 are in the on state. And again from this omega T2 to 2 pi, N3, N4 will be in the on state. After that, positive half cycle of the source voltage, again you need to trigger the P1, P2 and N1, N2, P3, P4, N3, N4. If you maintain the conducting periods of the SES like this, then you are able to collect F0 is equals to 2Fs. So what I observe here, if you go through the either bridge type cycloconverter or midpoint type cycloconverter, the output voltage waveform should be same. But the conducting periods of the switches or the conducting period of the SES can be changed. Like if you go through the midpoint type, if you have P1, bridge type P1, P2. If you have P2, P3, P4. That is the difference. And the operation point of view and output voltage point of view, there is no differences. The same output voltage waveforms can be observed for both midpoint type converter and bridge type converter. Output voltage should be same. And if you go through the step up cycloconverter and step down cycloconverter, construction point of view, these are same. That means the same midpoint type converter topology is used for either step up cycloconverter or step down cycloconverter. Depends upon the changing of the conducting period of the switches, we are able to collect either output frequency is lower the source frequency or higher the source frequency. Whether it is step up cycloconverter or bridge type cycloconverter, output voltage waveform should be same. What is the difference observed here? In midpoint type converter, only single SER comes to the on state at a time, whereas in bridge type converter, two switches will be comes to the on state. That is the main difference. So, coming to the summary of this class, in this class, we just explained the operation of single phase step-up cycloconverter with R load, both midpoint type and bridge type. And in the next class, we discuss the operation of single phase step-down cycloconverter with R and RL loads. Thank you.